Hello, AP Chemistry students. It's me, Dr. V, and it's time to review for the upcoming AP Chemistry exam. In this webcast, we're going to work on free response question number 2 from the 2023 exam. Now, you may already know this, but just in case you didn't, I wanted to point out that free response question number 2 on any AP Chemistry exam from the last decade is a long free response question. That means it's scored out of 10 points, and it could have as many as 7, 8, even 9 parts to it. They're really long questions. Grab your calculator, your periodic table, and your formula sheet. I say that because I want you to let me introduce each part of the problem, and then I want you to pause the webcast and try to answer that section on your own. And then resume the webcast and let me explain how I arrived at my answer. The reason for doing that is it will let you score your own work as you go. Did you earn the point? Did you not earn the point? What do you need to improve your answer? Remember, the goal here is for you to show all the chemistry knowledge that you've acquired in the last year. It takes practice. We're just going to get better as we go. Let's jump right into the problem. In the gas phase, aluminum chloride is a molecular substance. A reaction of gaseous aluminum chloride at high temperature is represented by the following balanced equation, and we're given the balanced equation. Part A asks, how many grams of chlorine can be formed from 1.25 moles of aluminum chloride? Now, I do want to point out that this is chlorine atoms and not molecular chlorine, right? So that's a little unusual. That's not the typical thing that we see in these problems. I like to set this up as a factor label. It's my go-to strategy. X grams of chlorine equals 1.25 moles of AlCl3. From the balanced equation, we see that for every AlCl3 that reacts, we get 3 chlorine atoms. So 1 mole of aluminum chloride gives me 3 moles of chlorine. But I want the mass of chlorine, so I need to multiply by the molar mass of chlorine. Remember, not diatomic chlorine molecules, but just chlorine atoms. And when I do that, I get an answer of 133 grams of chlorine. And that's the work you needed to show to get 1 point. Additional reactions that involve aluminum or chlorine are shown in the following table. So we had reaction 1, and now we've got 3 more reactions 2, 3, and 4. Part B says, calculate the enthalpy of reaction for reaction number 1 in kilojoules per mole using reactions 2, 3, and 4. I hope you recognize right away that this is a Hess's Law problem. We need to work backwards from reaction 1 and decide what to do with reactions 2, 3, and 4 to make them add up to reaction 1. They should do that, right? That's how Hess's Law works. We do it by looking at the reactants and products and comparing them. And for each reaction, we have to decide, do I want to keep it as written or do I want to flip it around? And do I need to multiply that equation by anything? I can do either or both. The first reactant in reaction 1 is the AlCl3. And the only reaction that has AlCl3 in it is reaction 2, which has it as a product. But in my target reaction, reaction 1, it's a reactant. So that tells me that I need to flip reaction number 2 around. When I flip a reaction, I also need to change the sign of delta H. So instead of being negative 583, it now needs to be positive 583. The next species in reaction 1 is the aluminum gas. And the reaction that involves aluminum gas is reaction 3. Reaction 1 has aluminum gas as a product. I know it seems so weird to think about aluminum gas, but just run with it. And reaction 3 also has as a product. They both have the same coefficient, so I don't need to do anything to reaction 3 as written. I'm just going to keep it as it is. And then my last product in reaction 1 is the chlorine atoms. And the reaction that's got chlorine atoms is reaction 4. Now, one thing I notice is that in the target reaction, reaction 1, the chlorine has a coefficient of 3. But in reaction 4, it's got a coefficient of 2. I do need everything to work out correctly, so that means I need to multiply all of reaction 4 by 3/2, or by 1.5 if you prefer. And when I do that to the equation, I also need to do that to delta H. And if I take the flipped equation 2 and equation 3 and reaction 4, where it's multiplied by 1.5, they do add up to reaction 1. And that means that their delta H's will also add up to the enthalpy change for reaction 1. So I'm just going to add them up the way I've manipulated everything, and I get an answer of 1,274 kilojoules. This question was worth 2 points. Essentially, 1 point was figuring out how to manipulate equations 2, 3, and 4, and the second point was for adding up all the values once you've done that manipulation. Part C. A potential energy diagram for diatomic chlorine is shown in the following graph. Part 1 of Part C says, based on the graph, what is the bond length in picometers for Cl2? Now I do notice that my x-axis is in picometers, so I'm just going to read off the graph. Specifically what I'm looking for here is what internuclear distance gives me the energy minimum. That's my average bond length. So the energy minimum, I'm pointing to it with my little red arrow here, you know I love my rainbow pen, is just at about 200 picometers, and that's actually my answer. So I'm just going to read that down the graph and write that down as my answer. I don't even need to give an explanation. I'm just reading it off the graph. And that was worth 1 point. There was a tiny bit of wiggle room. You could probably be off by as much as 5 picometers, but it really should be just about 200 picometers for your answer here. Part 2 of Part C goes on. A student finds that the average AlCl bond length is 220 picometers, and the average bond energy is 425 kilojoules per mole. Draw the potential energy curve for an average AlCl bond on the graph. So the key things we're looking at here is that the bond length is 220 picometers, so my energy minimum needs to be at 220 on my x-axis. The average bond energy is 425 kilojoules per mole, and that means on my y-axis, the minimum needs to go down to negative 425. And that's what my graph needs to look like. So here's the graph I drew. Notice that I've got my minimum between 400 and 450. It's as close as I could do for 425. And the minimum's right at about 220 on my x-axis. And then, finally, it levels off at about 0 as I approach 500 picometers, when those atoms are really far apart. Those are the 2 key features that we're looking for. 1 point for having your energy minimum go down to minus 425, 1 point for the average bond length being at 220. Part D. 3 proposed Lewis diagrams for the AlCl3 molecule in the gas phase are shown. Part 1 of Part D states, the AlCl3 molecule has a trigonal planar geometry. Which diagram, 1, 2, or 3, can be eliminated based on geometry? Justify your choice based on Vesper theory. So we do need to think about molecular geometries here. Well, Vesper theory, as we know, is all about how many electron domains are around the central atom. And we need a trigonal planar geometry. Trigonal planar geometries have 3 electron domains around the central atom. We've got the 3 diagrams. Let's look at what's going on with the aluminum in each one. In diagram 1, I see that there are 3 electron domains around the central atom. In diagram 2, we've got that lone pair on the aluminum. That's 4 electron domains. In diagram 3, also has 3 electron domains around the central atom. Double bonds still count as 1 domain. Sometimes students need to be reminded of that. So diagram 1 is consistent, and diagram 3 is consistent, but diagram 2 needs to be eliminated. The aluminum atom has 4 electron domains, and therefore it would have a trigonal pyramidal molecular geometry, and that's our justification for saying diagram 2 doesn't meet the expectations. And that's worth 1 point. There was a second part to Part D. Which of the 3 diagrams is the best representation for the bonding in AlCl3? Justify your choice based on formal charges. So formal charge calculations are really easy to do, but you have to make sure you do them correctly. It starts with the number of valence electrons that an isolated atom of that element would have, minus the number of bonds attached to that element, minus the number of non-bonding electrons attached to that atom. So I'm going to do a full calculation for the left-hand chlorine in diagram 1, just so you can see how it goes. All right, it's a chlorine atom, an isolated chlorine atom that has 7 valence electrons. It's got 1 bond on it. It's got 6 non-bonding electrons, 6 dots, right? And so the formal charge of the chlorine that I'm pointing to in diagram 1 is 0. In fact, all the atoms in diagram 1 have formal charges of 0. I'm not going to show the work for all of them because it'd be really tedious, but it's the same kind of calculation. I'm going to go ahead and assign formal charges for all the atoms in diagram 2 and for all of the atoms in diagram 3. And the best structures are the ones that have formal charges as close to 0 as possible. Diagram 1 has all its formal charges equal to 0, and that's preferable over non-zero formal charges, as we see in diagrams 2 and 3. All right. I have an issue with diagram 2 anyway, because the sum of the formal charges in diagram 2 is not 0, and it should be 0. It's not a reasonable structure, but that's not what the question asked us, so I'm trying to stay on target here. All right. That was worth 1 point for saying diagram 1 and backing it up because the formal charges are all 0. AlCl3 is known to dimerize reversibly in the gas phase. The dimerization equilibrium is represented by the following equation. So 2AlCl3 make Al2Cl6. And part E says, write the expression for the equilibrium constant Kp for this reaction. Things to watch out for. It's asking for a Kp expression. This needs to be in terms of gas pressures, partial pressures, and not square brackets. If you write square brackets, you won't get credit. We also have to remember we have to do products over reactants. Coefficients become exponents. When we follow all those rules, we get this. Notice it's the partial pressure of the Al2Cl6 over the partial pressure of the AlCl3, and I have to square that because it's got a coefficient of 2 in the balanced equation. And that was worth 1 point. A particle level diagram of an equilibrium mixture of AlCl3 and Al2Cl6 at 400 degrees Celsius in a 25-liter closed container is shown. So we can see there's a whole bunch of particles here. Altogether, it's 10 molecules. Using the particle level diagram, calculate the value of Kp for the reaction. The total pressure in the container is 22.1 atmospheres. We know what the Kp expression is. We just wrote that in part E. We need to know the partial pressures of the AlCl3. We need the partial pressures of the Al2Cl6. The equation that you need is actually on your formula sheet. We need the moles of Al2Cl6 over the total moles times the total pressure. All right, so we're using the mole fraction times P total. That'll give us the partial pressure of Al2Cl6. And we know that P total is 22.1 atmospheres. We were given that. So we need to work out the whole mole fraction piece from our particle level representation. Like I mentioned, there are 10 molecules total. When you get these particle level diagrams, count particles. It's always really helpful. When I look at the Al2Cl6, there are 3 of them out of the 10 total. So that means 0.3 times 22.1 is going to give me the partial pressure due to the Al2Cl6, which works out to be 6.63 atmospheres. The remaining 7 molecules must be the AlCl3. We're going to do the same kind of math, right? The mole fraction of the AlCl3 times the total pressure will give us the partial pressure due to AlCl3. So we've got the 7 AlCl3. If you don't believe me, you can always just count. So 0.7 times 22.1 will give me the partial pressure of the AlCl3, which is 15.5. Now that I've got these partial pressures, I'm going to substitute them into my Kp expression. I'm going to remember to square the partial pressure of the AlCl3 because I need to square it, and that's a thing students often will forget to do. I'm going to evaluate that, and I get an answer of 0.0276. That was worth 1 point. A lot of work for 1 point, right? That's the way it goes sometimes. How did you do? The average score on this question in 2023 was 5.22 points out of 10. So as AP long response questions go, fairly easy, manageable. If you scored 5 points out of 10, you're doing well. If you scored 6 or 7, you're in great shape. If you got 8, 9, or 10 points, good job. You should be really pleased with yourself. All right. If you didn't score quite the way you wanted to, go back and review equilibrium, go back and review Lewis structures. So many parts of this question, really a kitchen sink question. If you found this helpful, like the video and leave a comment. And don't forget to subscribe to my channel. I'll be posting more review videos. I've got a whole bunch of other review videos, and hopefully you'll find them helpful. Take care and have a good day, and keep studying chemistry.